Think about how much of our lives are just filled with sound, right? I mean, the environment telling us what's around, conversations connecting us, music.
Yeah, it's everywhere. Emotion, information.
It's this constant stream. But traditionally, when we've built AI to process all this, we've sort of treated each type of audio, speech, music, sound effects like a totally separate problem.
Which is pretty interesting because it really mirrors how we used to approach language, doesn't it?
How so?
Well, we had different tools for translation, different ones for summarizing, others for writing
Like
assistance.
separate tools for separate tasks.
Exactly. Then along came these huge universal language models, LLMs, that could suddenly handle almost any text-based task you threw at them.
Okay, I see the parallel.
And now that same kind of revolution seems to be starting in the world of audio,
And that's precisely what we're going to dive deep into today. We're looking at Kimi-Audio.
right? An open source model.
Exactly. And our mission for this deep dive, really digging into their technical report, that's 250.4.18425V1, if you're following along, is to understand what makes Kimi-Audio tick, what makes it different.
And what its potential impact could be, yeah.
Yeah, imagine one single model that can understand and generate pretty much anything audio related. That's the promise here.
Okay, so where do we start? The architecture.
Let's do it. Lay out the basics for us. What are the core components?
Okay, so fundamentally, Kimi-Audio has like three key parts. First up is the audio tokenizer.
Okay, tokenizer, taking raw audio and making it AI readable.
Pretty much, yeah. Converting it into a format the model can actually work with. Then you have the audio LLM itself, the large language model. That's the brain, the intelligence doing the processing.
Got it. Tokenizer, LLM, and the third.
Then finally, the audio detokenizer. This takes the LLM's output and turns it back into actual audible sound that we can hear.
Okay, tokenizer, LLM, detokenizer. Let's zoom in on that first step. How does it go from, sound waves to something the AI gets? You mentioned the tokenizer.
Right, and it's actually a really interesting hybrid approach they're using here. It's not just one type of information.
Hybrid, meaning?
It grabs two distinct kinds of audio info. First, it uses what they call discrete semantic tokens. Think of these as little chunks of meaning,
Meaning.
like words.
Sort of like the essence of the words, yeah.
Yeah.
Extracted 12.5 times every second, so a 12.5 hertz frame rate. And these actually come from another model, GLM-4 voice, based on automatic speech recognition, or ASR.
Okay, so 12.5 hertz semantic tokens from GLM4 voice. What's the other part of the hybrid?
Alongside those, you have continuous acoustic vectors. These come from a pre-trained whisper model.
Ah, Whisper. Known for being good at capturing audio detail, right?
Exactly. It gets the finer details, the textures, the how it sounds, not just the what. This whisper data is initially sampled much faster, but they downsample it to match that same 12.5 hertz rate.
So semantic meaning and acoustic texture, both at 12.5 hertz feeding into the LLM. Precisely. It's a clever way to get both the gist and the nuance. The semantic tokens give you the core meaning, like the transcript, while the acoustic vectors capture, the speaker's tone, background noise, the whole sound environment.
Which potentially gives a much richer understanding than just one type alone.
That's the idea. It helps the model not just transcribe, but maybe understand emotion, identify subtle sounds.
Okay, makes sense. So this combined representation hits the audio LLM. What's its main job then?
Its primary role is, well, processing all that audio data and then generating outputs. And crucially, it generates two kinds of outputs.
Two kinds.
Yeah, you can generate more of those semantic audio tokens for creating sound, but it also generates standard text tokens.
Ah, so it can output both audio information and text.
Exactly. That's key to its versatility. It lets it understand audio, create audio, and interact via text, like in a chat.
Very cool.
Okay.
And what's the structure inside this LLM? How's it built?
It's built using transformer layers, the standard architecture behind most big language models these days.
Right, the attention mechanism weighing importance.
Yeah, that's the core. What's interesting here is how they've structured it. The initial layers are shared.
Shared, meaning they handle both audio and text input.
Correct. If the input includes both audio representations and text, these first layers process them together. Then, after these shared layers, the model branches out
Branches out.
into two separate heads. One head is specialized for generating text output, and the other head is specialized for generating those discrete audio semantic tokens.
That sounds like a really efficient design. How did they get this thing started, like the initial setup?
Yeah, the initialization strategy is quite smart. They didn't start everything from scratch.
Okay.
The shared layers in that text generation head,
Yeah.
they actually copied the weights directly from an existing powerful text LLM. Specifically, Quen 2.57b.
Ah, so they borrowed the language capability from a model that's already good at text.
Exactly. It gives Kimi-Audio a huge leg up on understanding and generating language right from the start.
Makes sense. And the audio head.
That part was initialized randomly. So it had to learn the audio generation patterns from the ground up during training, but the text side already had a strong foundation.
Okay, so we've got audio in, processed by the LLM, outputting semantic tokens or text. Now, how do those semantic tokens become sound again? That's the detokenizer's job.
That's right. The audio detokenizer takes those semantic audio tokens from the LLM and reverses the process, turning them back into sound we can hear. And this happens in two main stages.
Two stages, okay.
First, there's a process called flow matching. It takes those 12.5 hertz semantic tokens
Yeah, 12.5 per second.
and effectively upsamples them, increases their rate, to create 50 hertz Mel spectrograms.
Mel spectrograms. Remind us what those are.
Think of it like a detailed picture of the sound. It shows how the different frequencies in the audio change over time. It's a visual representation that captures a lot of the detail needed for realistic sound.
Okay, so flow matching creates this detailed sound picture. Then what?
Then, a vocoder takes over. They use one called Big VJAN. The vocoder's job is to take that Mel spectrogram, that picture, and synthesize the actual audio waveform from it. You know, the thing your speakers actually play.
Gotcha. Flow matching to spectrogram, vocoder to waveform. Now, the report mentioned something about streaming and look ahead. How does that fit in? Sounds important for making it feel responsive.
It is, yeah. For things like real-time conversation, you can't wait for the whole response to be generated. So they developed a chunk-wise streaming detokenizer.
Chunkwise, so it processes in small pieces.
Exactly. Instead of waiting for the entire sequence of semantic tokens, it processes them in small chunks. But just doing that can create awkward joins between the chunks.
Right. You might hear little glitches or unnatural pauses.
Potentially, yes. So they added a look-ahead mechanism. When it's decoding one chunk, it actually peeks ahead at a few of the semantic tokens from the next chunk.
Ah, okay. So it anticipates what's coming.
Precisely. That little bit of look-ahead allows it to smooth out the transitions between chunks, making the generated audio sound much more seamless and natural without adding much delay overall. It just adds a tiny bit of latency right at the very start.
That's a clever solution. Okay, so that's the architecture. But a model like this is nothing without data, right? What did they feed this thing?
Oh, the data curation
Absolute.
well, it's massive. The scale of the pre-training data is honestly staggering. We're talking over 13 million hours of diverse audio.
13 million hours.
Yep. Audiobooks, podcasts, interviews, just a huge mix covering speech, general sounds, music, everything.
Wow. And was it just audio?
No, they also included a large text-only dataset, something called Moonlight, specifically to train the language understanding parts.
Okay, 13 million hours of audio plus text data. How on earth do you even process that much raw audio? You can't just feed it straight in, can you?
No, definitely not.
Yeah.
They built a sophisticated automatic audio data processing pipeline. It's a multi-step process to clean it up and extract useful info.
Okay, what are the steps?
First, they often apply speech enhancement. They use a technique called band split RNN to try and reduce background noise, echoes, that sort of thing.
Make it cleaner.
Yes, but interestingly, they don't always do it. It's about a 50-50 random choice whether to use the enhanced version or the original audio for any given segment.
Huh. Why not always clean it?
Well, our guess is it helps the model become more robust. It learns to handle both clean and slightly noisy real-world audio. Plus, you don't want to strip out all the background context sometimes.
That makes a lot of sense, actually. Okay, so after potential enhancement.
Next comes diarization, figuring out who is speaking when.
Right, speaker A, speaker B.
Exactly. They use a tool called Pianote for the initial pass, but then they have a bunch of clever post-processing steps to refine it. Things like merging speaker clusters, if the system thinks two labels are actually the same person, fixing short segments that might have been misattributed, and merging adjacent segments from the same speaker if the gap is short. They try to get segments up to about 27 seconds long or until there's a 2-second silence.
So, pretty sophisticated speaker labeling. Now they know who's talking, the audio might be cleaner. How do they get the actual words, the transcript?
Right, that's the speech transcription step. They use Whisper Large V3, a very powerful ASR model. It first detects the language they focus mainly on English and Mandarin.
Okay.
For English, Whisper handles the transcription and can even add punctuation fairly well. For Mandarin, they use another model, Paraformer Z. Now this one gives character timestamps, but doesn't add punctuation automatically.
So how do they handle punctuation for Mandarin?
They developed a rule-based system. It looks at the time gaps between the timestamp words or characters and inserts commas or periods based on the length of the silence.
Wow, that's a lot of detailed engineering just to prepare the data.
It really is. And you can imagine the computing power needed for all this.
I was just about to ask, processing 13 million hours.
Yeah, they mentioned using a cluster of 30 cloud instances, serious hardware, lots of CPU cores, RAM, and importantly, GPUs. They specifically mentioned Intel Xeon Platinum processors with something called advanced matrix extensions.
And how much could they churn through?
Their setup allowed them to process around 200,000 hours of raw audio per day.
200,000 hours a day. Okay, that explains how they got through 13 million hours. So that's the massive pre-training data set. Then they moved to supervised fine-tuning, or SFT.
Correct. After the model has learned general patterns from that huge data set, SFT focuses it on specific tasks and following instructions.
And what kind of data did they use for this SFT stage?
They organize it into three main buckets. First, audio understanding tasks.
Like what?
Things like more ASR, audio question answering, AQA, audio captioning, AAC, describing sounds and words, speech emotion recognition, SER, sound event classification, SEC, and audio scene classification, AFC, like, is this a street, an office, a forest?
So basically everything related to understanding what's in the audio.
Pretty much. They used a ton of existing open source datasets for this. The list is huge WANET speech, audio caps, FSD 50K, IEMO cap, TT datasets, Urban Sound 8K, many, many more. Plus, they added about 55,000 hours of their own ASR data and over 5,000 hours of in-house AAC and AQA data. And they fine-tuned on all of this. Yeah, typically running through each dataset between 2 and 4 times what they call epochs.
Okay, that covers understanding. What was the second SFT category?
Speech conversation. This is where it gets really interesting in how they generated the data.
Oh, how'd they do it?
They wanted lots of multi-turn dialogues. So for the user side of the conversation, they actually prompted other large language models to generate queries, questions, typical user things.
Okay, using LLMs to generate user text.
Right. Then they converted that text into speech using their own text-to-speech system called Kimi-TTS. And this TTS is apparently quite something. It's a zero-shot TTS. It only needs like a 3-second audio prompt of a voice, and it can then generate speech in that voice. And they claim to have a library of over 125,000 different timbres they could use for these user utterances.
Whoa, 125,000 voices. That's incredible diversity for the user side. What about the AI assistant's voice in these conversations?
For the assistant, they went the other way. Consistency. They picked one single professional voice actor to be the designated Kimi-Audio speaker.
Okay, one specific voice for the AI.
Yes, and they recorded this actor performing in over 20 different speaking styles and emotional tones, things like happy, sad, empathetic, formal, excited, each with 5 different levels of intensity.
Wow, that's very granular control.
Yeah, they even had a director overseeing the recording sessions with reference audios to ensure quality and consistency for each style and intensity level.
So the assistant's responses were synthesized using this specific voice actor's recordings, matching the required style and emotion.
Exactly. But what if they had existing audio they wanted to use, but needed it to be in the Kimi-Audio speaker's voice?
Good question. Voice cloning.
Sort of, yeah. They developed a system called Kimi-VC for voice conversion.
Kimi-VC.
Its job is to take speech from any voice and convert it into the timbre of that main Kimi-Audio speaker, but, and this is the cool part, while preserving the original speaker's style, emotion, and even their accent.
Wait, really? It keeps the accent and emotion, but changes the fundamental voice?
Apparently so. They built it on an existing framework called SeedVC and then fine-tuned it heavily using all that data they recorded from the main Kimi-Audio voice actor.
That sounds incredibly powerful, almost like digital puppetry for voices. Okay, that covers speech conversation data. What was the third SFT category?
The third was audio-to-text chat.
So audio input, text output in a chat format.
Right. And here they cleverly repurposed existing text-based instruction following datasets. Things like Magpie Pro, Evil Instruct, Open Hermes datasets designed to teach LLMs to follow text instructions.
How did they make that work for audio?
They took the user prompts or questions from these text datasets and converted them into speech using Kimi-TTS again, using a variety of different voices to simulate different users.
Okay, user query becomes audio and the assistant's response.
That remained as text, so the training data became pairs of spoken user input and written assistant output.
Did they modify the text data at all?
Yeah, they did some pre-processing. They filtered out text that was maybe too complex or relied heavily on formatting like long code blocks or tables. They also tried to rewrite some instructions to sound more colloquial, more conversational, and they converted some simple single-turn Q&A pairs into longer multi-turn dialogues.
Got it. And they fine-tuned on this synthesized audio text data.
Yep, for about 2 epochs.
All right, so we've got the architecture, the incredible amount of pre-training data, and the targeted SFT data. Now, how did they actually train this thing? Let's start with the pre-training phase. What specific tasks were involved?
The pre-training tasks were really designed to teach the model 3 things: understanding text alone, understanding audio alone, and crucially, how to connect the two.
Okay, makes sense. What were the specific tasks?
They broadly fall into those 3 categories. First, unimodal pre-training. This involved text-only training, just predicting the next text token using that Moonlight dataset.
Standard language model training.
Exactly. And also audio-only training, where the model listened to audio and tried to predict the next semantic audio token in the sequence, just learning audio patterns.
Okay, unimodal, text-only, audio-only. What was the second category?
Second category was audio-text mapping, connecting one modality to the other.
Like speech to text.
Precisely. One task was audio to text, which is essentially ASR training. Input audio, predict the text transcription. The model is only judged on how well it predicts the text.
And the reverse, text to speech.
Yep. The other mapping task was text to audio. Input text, predict the sequence of semantic audio tokens that represent that speech. Here, it's only judged on predicting the audio tokens correctly.
Okay, mapping covered. What was the third category? You said connecting them.
Right. The third category was audio-text interleaving, really mixing them together in the input and output.
Interleaving. How did that work?
They had 3 specific tasks here. One was called audio to semantic. The input would be a mix of raw audio chunks and some known semantic audio tokens, and the model had to predict the missing semantic tokens.
Okay, filling in the audio blanks.
Kind of, yeah. Another was audio to text, similar idea, but the input alternated between raw audio and text segments, and the model had to predict the missing text segments.
Filling in the text blanks based on audio context.
Exactly. And the third task, maybe the most complex, was audio to semantic and text.
Both at once?
Both at once. The input alternated between raw audio chunks and a mix of both known semantic tokens and known text tokens. And the model's job was to predict the missing semantic tokens and the missing text tokens.
Wow, that sounds challenging.
It is. They actually noted a specific difficulty here. Predicting the very first few semantic audio tokens in this combined task was hard. So they used a little trick.
Oh, yeah.
They added 6 special blank tokens right at the start of the semantic audio sequence, just giving the model a tiny bit of buffer or lead-in time to figure out the audio context before having to predict the first real semantic token.
Interesting. A little nudge for the model. Okay, that's a comprehensive set of pre-training tasks. How did they combine all this in the actual training run? What was the recipe?
So the overall recipe involved first initializing the audio LLM, as we discussed, using Qwen 2.57b for the shared layers and text head. They expanded the vocabulary to include all the audio semantic tokens and those special tokens.
Right.
Then they trained the model on all those different pre-training tasks simultaneously, but not equally. They assigned different weights to each task's contribution to the learning process.
So some tasks were considered more important.
Seems so. For instance, the text-only task had a higher weight than the audio-only task. The specific ratio they mention is 1 for audio-only, 7 for text-only, and then 1 for each of the mapping tasks, ADT, T2A, 1 for audio to semantic, 1 for audio to text, interleaved, and 2 for the combined audio to semantic and text task.
Okay, specific weighting. How much data did they train on?
They trained for 1 full pass of 1 epoch over a data set comprising 585 billion audio tokens and 585 billion text tokens.
Billion with a B. Just,
Oh.
wow. And the technical details. Optimizer. Learning rate.
Standard stuff mostly. Adam W. Optimizer. The learning rate started at 2E5 and decayed down to 2E6 over the course of training using a cosine schedule, with a short warm-up period at the beginning covering about 1% of the total tokens.
Anything else notable about the pre-training setup?
One interesting detail is how they handled the Whisper feature extractor, the part that generates the continuous acoustic vectors. They initialized it using the weights from Whisper Large V3, but they kept it frozen for the first 20% of the pre-training.
Frozen, meaning its weights weren't updated.
Correct. They let the rest of the model start learning, while keeping the initial audio feature extraction fixed. Then, after that first 20%, they unfroze it, allowing the Whisper part to also be fine-tuned, along with everything else for the remainder of pre-training.
Huh. Wonder why they did that. Maybe to stabilize early training.
Could be. Or perhaps to ensure the model first learned to use the features as Whisper intended before letting it adapt them. Okay, so that's pre-training. What about the supervised fine-tuning SFT recipe? How did that differ?
Yeah, what was the approach there?
The main goal for SFT was teaching the model to follow instructions effectively. A key decision they made was not to use any special tokens or signals to tell the model, okay, now do ASR or now do TTS.
No task switching signals. How did it know what to do?
Just through natural language instructions.
Yeah.
Every single task, every example was framed with a natural language instruction.
Like transcribe this audio or answer this question based on the sound.
Exactly. And to make it more robust, they generated two versions of each instruction. One as text and one spoken as audio, using their Kimi-TTS system. During training, they'd randomly pick either the text or the audio version of the instruction.
Clever. Did they vary the instructions too?
Yes, significantly. They created around 200 different phrasings for ASR instructions and about 30 variations for the instructions for other tasks. For each training sample, they'd randomly select one of these variations. Keeps the model from just memorizing specific phrases.
How much SFT data do they use in total?
The paper mentions around 300,000 hours across all the different SFT datasets we talked about earlier.
Okay. And the training specifics for SFT?
They fine-tuned the model on each specific SFT data source for about 2 to 4 epochs. Again, using the Atom W optimizer, but with a lower peak learning rate, this time starting at 1E5 and decaying to 1E6, with a slightly longer warm-up covering 10% of the tokens.
Got it. And one last training piece, the audio detokenizer itself, that needed training too, right?
Absolutely. That was trained separately in 3 distinct stages.
3 stages for the detokenizer.
Yep. Stage 1 was pre-training both the flow matching part and the Big VJN vocoder. They used about 1 million hours of their general pre-training audio data for this, just to get the basics of audio generation down.
Okay. General pre-training. Stage 2.
Stage 2 was chunk-wise fine-tuning, again on that same large data set. But here, they dynamically varied the size of the audio chunks during training, teaching the detokenizer to handle different segment lengths smoothly, like we discussed for the streaming aspect. Chunk sizes varied from half a second up to 3 seconds.
Preparing it for streaming. And the final stage.
Stage 3 was fine-tuning specifically on high-quality recordings of just one speaker, that main Kimi-Audio voice actor.
Ah, specializing it for that target voice.
Exactly. This final stage ensures the detokenizer can produce really clear, expressive, and consistent speech in that specific Kimi-Audio persona voice.
Okay, wow. That is a truly massive and intricate process for building and training this model. So the big question, did it work? How do we know if Kimi-Audio is actually any good? Let's talk evaluation.
Right. And evaluating these big audio foundation models is, no, it's actually a bit of a minefield. It's a known challenge in the field right now.
How so? What makes it tricky?
There are a few things. Different research groups sometimes calculate metrics, even common ones like word error rate for ASR, slightly differently, making direct comparisons hard.
Inconsistent metrics. Okay.
Also, models are often evaluated under very different conditions, different hardware, different prompting strategies. And maybe the biggest issue is the lack of really good standardized benchmarks for evaluating the quality of generated audio, especially for conversational speech.
So lots of variability and gaps in how models are tested. How did the Kimi-Audio team address this?
They took a really commendable step, actually. They developed and open sourced their own evaluation toolkit, specifically for audio foundation models. It's on GitHub.
An open source toolkit, what does it do?
It aims to standardize things. It supports Kimi-Audio, obviously, but also several other recent audio LLMs. It provides standardized implementations for metrics like where. For more subjective tasks like audio question answering, it even incorporates using GPT-4o Mini as an intelligent judge to evaluate the quality of the answers, going beyond simple text matching.
Using another AI to judge. Interesting.
Yeah. And it provides a unified platform, trying to level the playing field by defining standardized inference parameters and prompting methods. They call these recipes for each model, so you're comparing them more fairly.
That sounds incredibly useful for the research community.
It really is. They even went a step further and created a completely new evaluation benchmark, focused specifically on speech conversation quality.
What does that benchmark measure?
It uses human evaluators to assess things like how well the model controls the emotion in its generated voice, how empathetic it sounds, its ability to control speaking speed, and the overall naturalness and quality of the conversation.
Okay, so they built the tools for a fair fight and even added a new conversational benchmark. What were the results? How did Kimi-Audio perform using this setup?
The results they report are pretty impressive across the board.
Let's start with the basics. Automatic speech recognition, ASR. How accurate was it?
It showed really strong performance, consistently outperforming previous state-of-the-art models on a whole range of standard ASR benchmarks. LibreSpeech, both clean and other, Fleurs in English and Chinese, A shell 1 and 2, win at speech.
Outperforming models like Quen-Audio, Baichuan-Audio.
Yes, and others like Step Audio and the newer Quen 2.5 Omni. In many cases, the word error rate, WER, was significantly lower for Kimi-Audio, meaning fewer transcription mistakes. They also tested it on their own internal ASR test sets and saw strong results there too.
Okay, very strong on ASR. What about broader audio understanding, sounds, music, not just speech?
Also very strong. They tested it on benchmarks like MMAU, which covers music, general sounds, and speech understanding. Also on Clotho AQA for audio question answering, vocal sound for classifying different types of vocalizations, non-speech 7K for non-speech sounds, MELD for emotion recognition in conversations, TUT datasets for sound event detection, cockle scene for audio scene classification.
Wow, a wide range. And the results.
Again, it generally outperformed the baseline models they compared against across these diverse understanding tasks.
Okay, understanding looks good. What about its ability to chat using audio input? The audio-to-text chat capability.
Tier 2, it achieved state-of-the-art results on a benchmark called Open Audio Bench, specifically on subtasks like Alpaca-Eval, Llama Questions, and Trivia QA. It also performed strongly on reasoning QA and web question tasks within that benchmark.
And any other chat benchmarks?
Yes, they also evaluated it on Voice Bench, which is another comprehensive suite. Kimi-Audio consistently outperformed comparable models there across tasks, covering valuation, common sense reasoning, question answering, instruction following, and even identifying harmful content.
So top-tier performance in text-based chat driven by audio input. Now, what about the really hard part, the full speech conversation judged by humans?
Right, using that new benchmark they created. The human evaluators gave Kimi-Audio very high scores, particularly for its ability to control the emotion and speed of its voice, and also for perceived empathy.
High scores. Compared to what?
They compared it against models like GPT-4 Mini, Step Audio Chat, GLM-4 Voice, and even the full GPT-4o. While GPT-4 edged it out slightly in overall average score, Kimi-Audio performed very strongly, significantly outperforming the other audio-focused models, and demonstrating that its generated speech is not just understandable, but also expressive and controllable in a conversational context. It was rated very close to GPT-4o overall.
That's really impressive, especially being close to a model like GPT-4o and human perception of conversation quality. Okay, so Kimi-Audio seems like a major player. How does it fit into the broader landscape? What's the related work here?
The report does a good job contextualizing it. They trace the evolution from specialized audio models, separate tools for ASR, TTS, understanding towards these more universal, general-purpose audio AI systems, which is where Kimi-Audio sits.
Who else is working in this universal audio space?
Well, they mentioned several lines of related work. Their models focus primarily on ASR and audio understanding, like Whisper itself, the Quen-Audio series, SAML, OSUM. These are great at understanding, but often have limited or no audio generation capabilities.
Okay, understanding focused models. What about generation?
Then you have models primarily focused on TTS or audio generation, like Google's Audio LM, Microsoft's Valley, or others like LSCC Uni-Audio VoiceBox. These excel at creating audio, but often lack deep understanding or conversational abilities beyond simple TTS.
So understanding on one side, generation on the other. Any others trying to bridge the gap?
Yes, there's also work specifically on speech conversation and real-time dialogue systems models like Moshi, GLM-4 Voice, which Kimi uses internally, Mini-Omni, OmniFlat, and Llama Omni. But these are often focused just on speech, maybe not broader audio, and sometimes compromise on the underlying language modeling power to achieve low latency I.
So how does Kimi-Audio position itself against these other universal models that try to do it all, like Baichuan-Audio or Step Audio or Quen 2.5 Omni that you mentioned earlier?
They highlight a few key differentiators. Compared to Baichuan-Audio, they suggest Kimi-Audio is perhaps more balanced across speech, sound, and music, whereas Baichuan might be more speech-centric. Compared to Step Audio, Kimi-Audio is smaller, open source, and relies less on potentially limiting synthetic data for training, whereas Step Audio is massive and uses a lot of synthesized speech. Compared to Quen 2.5 Omni, while Omni focuses heavily on streaming, Kimi-Audio might have an edge due to its significantly larger pre-training dataset.
So Kimi-Audio's niche is...
They emphasize being universal and open source, supporting all the core audio tasks, understanding, generation, conversation, the unique hybrid input, the dual generation heads, the efficient chunk-wise detokenizer, and especially that massive, diverse, multimodal pre-training combined with careful instruction fine-tuning. They see this combination as leading to their state-of-the-art results.
It definitely sounds like a very comprehensive and well thought out approach, but no model is perfect. What limitations do they acknowledge, and where do they see things going next? What are the challenges?
They point out a few key challenges and future directions. One major limitation they discuss is the current pre-training's heavy reliance on ASR transcriptions for the semantic meaning.
Why is that a limitation?
Because ASR text captures the words, but it misses so much else, the paralanguage, right? The speaker's tone, emotions, style, sarcasm, plus background sounds, the acoustic scene, all that context gets lost in just a plain text transcript.
So how could that be improved?
They suggest that incorporating more descriptive text representations, like detailed audio captions that describe the whole sound scene, including non-linguistic elements, could be really important for future pre-training.
Get richer text descriptions than just ASR. What else?
They also talk about the limitations of the current audio representations themselves. The discrete semantic tokens are great for transcription-related tasks, and the continuous acoustic vectors are good for reconstruction, but neither perfectly captures everything.
So we need better ways to represent audio.
Ideally, yes. They propose developing new representations that can somehow integrate both the high-level semantic meaning and the low-level acoustic details more effectively within a single framework.
That sounds like a fundamental research challenge.
It definitely is. And perhaps the biggest challenge they raise relates to the data sources themselves.
How so? Didn't they use 13 million hours?
They did, but much of the learning signal, especially for connecting audio and text, still relies on the outputs of existing ASR and TTS systems used during data preparation or SFT data generation.
And that's a problem because...
Because it potentially creates a ceiling. The model can only ever be as good as the ASR and TTS systems used to create its training data. It's learning from their outputs, not necessarily the raw audio intelligence itself.
Ah, I see. It's learning secondhand information in a way.
Exactly. So they envision a future direction where models are trained more directly on native, raw audio data, learning the connections and structures autonomously without being quite so dependent on intermediate ASR-TTS steps. That, they suggest, might be the key to unlocking truly autonomous audio intelligence that surpasses the limitations of current helper systems.
Training directly on the world sounds, essentially. Okay, so summing up, Kimi-Audio really does seem like a significant leap forward, doesn't it? A very versatile, powerful, and notably open source model pushing the boundaries in understanding, generating, and even conversing with audio.
Absolutely. It's a major contribution. And the fact that they've released not just the model checkpoints, but also the code and those evaluation tools we discussed is huge for the community.
Yeah, it really lowers the barrier for others to experiment, build upon it, and push this field forward collectively.
Definitely encourages further exploration and contribution.
It really leaves you wondering, doesn't it?
Right.
What is the ceiling here? Could we actually reach a point where AI truly perceives and understands the full richness of our auditory world? You know, the subtle emotion in a voice, the story told by a city's soundscape.
Its potential is enormous.
And what would that mean for how we interact with technology, with information, with each other even? It's definitely something to ponder, a fascinating space to watch.